Hello, my name is Denis Firsov, and in the following I am going to tell how to construct a multiple time signature scheme from one-time signatures and timestamping. This is a joint work with Henri Lakk and Ahto Truu. Recently, due to the increasing quantum threat, the interest towards post-quantum signatures has started to grow. This also induced an interest towards hash-based signatures, as it is believed that hash-based constructions have a good chance of staying secure in post-quantum era. However, efficiency, both time and space, is a concern for hash-based signatures. Reflecting on that, Buldes, Lanoia and Truu realized that since all legally binding signatures must be time-stamped, then it should be possible to optimize the construction of hash-based signatures by relying on the properties of timestamps. This resulted in a new type of server-assisted hash-based signature schemes designed around timestamping. We will refer to them as the BLT family. Unfortunately, original BLT schemes have either expensive key generation or stateful client-side computations. So, our goal is to design a new BLT scheme so that all client-side computations are efficient and also formally prove existential unforgeability in the multiple time setting. Let us start by looking at the basics behind cryptographic timestamping. The main goal of timestamping is to prove that a data object existed before a particular time. The common approach to this problem is to simply use a trusted third party like a notary. However, there are also approaches which do not require trusted third parties. For example, guard times KSI blockchain timestamping works in rounds of 1 second. During a timestamping round, the queries of users are aggregated into a Merkle tree, and the root of the resulting tree represents an accumulator of all the elements which were timestamped at that round. The proofs of inclusion into the accumulator are distributed back to the users. Later, aggregation blocks corresponding to different rounds are also combined together into an ever-growing binary tree, which is here called a calendar blockchain. Finally, to tie timestamps to real physical time, the current root of the calendar blockchain is published in widely accessible media like newspapers. The main property of timestamping services is backdating resistance. Intuitively, it means that if at current time we produced a fresh data object, then it must be infeasible to get a valid timestamp associated with some time in the past. Formalizing this idea is quite tricky, since it requires making it precise what it means for object to be fresh, and therefore is related to the notion of entropy. In this work, we will rely on the ideal model of timestamping, which can be seen as the following stateful module He. The state of the module consists of the variable t, which represents the current time, and the variable m, which is a map from time values to data objects. A user of timestamping service can perform timestamping query and timestamp checking query. Compared to an actual timestamping service, the module He is more permissive in the sense that in a timestamping query, the user supplies both the data object and the time to which he wants the object to be associated with. However, the module will reject the query if the supplied time value is in the past. This model preserves the unidirectional property of time in a way we can work in EasyCrypt. The second ingredient of the BLT schemes is a tag system. Functionally, tag systems are similar to digital signatures and also consist of a triple of polynomial time algorithms G, T, and V. G is a public secret key pair generation algorithm. T is a tagging algorithm which takes a secret key, a time value, and produces a tag which is associated to the time value. V is a verification algorithm which takes a public key, a tag, and a time value. We say that tag system is correct if for any valid tag key pair, the tag generation algorithm agrees with the tag verification algorithm. The main motivating property of the tag systems is forward resistant. It claims that if adversary observed a tag associated with the time t, then he must be unable to produce a tag which would be associated with any later time. It should be easy to see that forward resistance is strictly weaker security property than the standard existential unforgeability of digital signatures. Now we are ready to see how timestamping could be combined with a tag system to result in a signature scheme. To start with, the user must choose a backdating resistant timestamping service he and a forward resistant tag system T. The BLT key pair coincides with the key pair generated for the tag system. To sign a message M, first the user queries the timestamping service for the current time. Let us call it T. Second, the user produces a tag tau associated with the next time, say T+1. Third, the user binds the tag tau with the message M by timestamping the pair. Finally, the user outputs the pair of tau and T+1 as a signature on M. To verify message M against the signature tau T, the user must first verify the tag tau and the time T against the public key PK. Second, the user must query the timestamping service to check that the pair of the tag tau and the message M is indeed associated with the time T. We proved that the described signature scheme is existentially unforgeable. More specifically, if the timestamping repository is trusted, then the probability of an adversary performing a forgery is bounded from above by the probability of breaking the forward resistance of the tag system. Intuitively, if a user observes a signature tau M associated with the time T, then to perform a forgery he must produce a pair which is going to be associated either with the earlier time or with the later time. The first possibility is excluded by the backdating resistance of the timestamping service, and the second possibility is excluded by the forward resistance of the tag system. The presented BLT construction is secure for any forward-resistant tag system. In the following, we will see how to construct a specific multiple-time stateless and efficient tag system from one-time signatures. Let us first revisit the well-known Goldreich signature scheme, which was first described in the 80s. Goldreich showed that any one-time signature scheme S could be turned into a stateless multiple-time signature scheme. The main idea is to use trees of predefined height and sign user messages by using the key pairs associated with the leaves of the tree. The internal key pairs are used to authenticate public keys of their children. Overall, the public key of the Goldreich signature scheme is the public key associated with the root, and the secret key consists of all secret keys of all nodes. To exclude reuse of one-time signatures and while avoiding stateful computations, the trees must be sufficiently high and user messages must be associated with leaves pseudo-randomly, say by using the hash of the message as an address of the leaf to be used. A shortcoming of this approach is that the resulting signatures tend to be very large. Let us now go back to tag systems. Recall that the tag system is only required to prevent deriving tags for later times from tags associated with earlier times. As a result of this observation, we use an authentication tree similar to the one proposed by Goldreich. However, with every node in this tree, we associate a time value counting top-down, left to right. Therefore, every authentication path becomes uniquely associated with a time value. Moreover, as allowed by forward resistance, it becomes possible to deduce tags associated with some of the prior times, but not with the later ones. Our tree is potentially infinite. The public key of this tag system is the public key associated with the root. The secret key consists of all secret keys in a tree. We proved that the presented tag system is indeed forward resistant, and the tag system with n pre-generated independent secret keys is bounded from above by n times e, where e is the probability of breaking the existential unforgeability of the one-time signature scheme. In practice, we expect key pairs to be derived in a pseudo-random fashion, which drops the security level by the indistinguishability of the PRF. Finally, we want to mention that all our definitions, constructions, and claims are fully formalized in the EasyCrypt framework. Our formalization only required standard techniques. More specifically, adversaries are modeled as computations satisfying abstract interfaces. Probability claims are relative to each other. As a result, we must manually verify the complexity of transformations. Security protocols are modeled as imperative programs. Proofs are done using the standard game rewriting technique via probabilistic relational Hoare logic. Due to the support of SMT solvers, proving pure mathematical statements as well as properties of the functional programs and data structures is easy. Moreover, proofs also survive changes in the implementation. The hardest and most fragile are proofs about distributions, for example key generations, which are defined as imperative programs. Thank you for your attention.